Hello, welcome back. This section we're going to start talking about refraction. Now we'll talk a lot more about refraction when we get to chapter 30 and talk about lenses. But when a wave that is traveling at an angle changes its speed when crossing a boundary, it bends. So if there was, say, in this example, if there was a temperature boundary or a medium shift right here, and it bent because it changed speed, if it changes speed, it bends, and that bending is caused by refraction. And that changing of speed can happen when a temperature shift occurs or when a medium shift occurs. So there are lots of different ways that you can get refraction. For instance, think about this. If I have a lawnmower and I'm on a sidewalk and then all of a sudden I hit grass, the wheels that are towards the grass are going to slow first, and these wheels are going to continue fast. And since these wheels haven't slowed down yet, it bends. So you bend towards a slower medium. When you go into a slower medium, you bend towards it. If I was going the other way and I was going towards the faster medium, then the inner wheel would hit it first and would speed up. So you bend away from the normal being this line. You bend away from the normal when you go from slow to fast. You bend towards the normal when you go from fast to slow. So refraction is that bending that occurs when you change speed in different mediums. So refraction is the bending of a wave as it crosses the boundary between two media at an angle. You have to be at an angle, and the medium have to have different what we call indices or indexes of refraction. And that just means that the wave that you were talking about travels at a different speed in each one, and the ratio of those speeds is called the index of refraction. And as long as that index is not 1, because if it's 1 then the speeds are the same, but as long as that ratio is not 1, then you change direction. So here you see an example of waves refracting at a depth change in water, usually because temperature change happens as you get into deeper water, but also you have differences in water pressure, so things that cause that bending. When you go from one medium, even though it's still water, it's a different type of water, or the water has different properties. So when you hit that boundary, if you slow down, you shift towards that normal curve. So you see this shifting happen here. And keep in mind that the waves here, people get confused with water waves. The wave is not this line that goes up and down. The wave is the distance between these two crests. The wave is the way the energy is traveling. The energy in this wave at the bottom left is going from left to right. But when you hit here, you can see that the ray actually shifts. So first it was going straight right, and then it bends upwards. It bends towards the normal, which is the boundary, and the normal is the perpendicular line between the boundary that's formed. So we call each of these waves a wave front. So these wave fronts make it very visible. So a wave is the distance from crest to crest, but this line, these lines are the wave fronts. So the wave here would be from here to here. So that's a wave, that little distance. I think you can see my arrow. The wave front is this longer line. So don't get wave fronts confused with the actual wave. And the wave travels in the direction that the energy is traveling, which is left to right. So what causes a wave to bend? Changing speeds, changing medium, changing temperatures. So sound waves can be refracted as well. So notice here that I have warm air and cold air, and in cool air you're slower and you bend towards the slow. So like remember that you bend towards the slower grass. The grass slows you down, so you bend inward when you slow down. Whoops, I'm going the wrong way. So you see this with air too. When there's warm ground and cool air, like let's say a rain front is coming in and the air cools down and you holler out for your dog and your dog doesn't come. The dog may not even hear you, even though they have great hearing, because your sound will actually refract. Sound is a wave. It will refract upwards towards the cold air. Now, on a warm day, when the air is cool, or when the ground is cooler, you can actually, the dog can hear you a long way. And a good example of that is like when you have a cold lake. So at nighttime, the lake stays warm and the air stays cool. So since the air is cooler and the lake is warmer, if it's a warm day, then this actually should be the other way around. But if you have, so since the air is cooler over the surface of the lake, um, so here it's cold and here it's warm. Their description isn't good, but since the air here is cooler, you get cool air above the lake because the lake is cool. And if the air is warm, okay, so if the air is warm and the lake is cool, when that happens, you can actually hear sound over a lake. But I think this is the better showing. It'll bend towards the cool air wherever that cool air is. So what causes sound waves to refract? Usually it's a difference in temperatures of the air, because you're not going to, you could change the air itself, but um, another thing that can cause sound waves to refract is when they go from one medium to another. Like first it's in air, then it's in liquid. When it goes from like air to water, it's going to refract because it's going to change speed. It's actually going to speed up when it hits the water. Light will do the same thing. So due to refraction of light, swimming pools appear shallower than they actually are. A pencil in a glass of water appears to bend, right? You've probably seen many of these things. And the reason for that is, for instance, light travels slower in water. Sound travels faster in water, but light travels slower in water. So it actually bends towards the normal, and that makes this water appear less deep, because normally the light would go all a farther distance, but it gets bent towards the normal, so it doesn't look as deep. So here the light goes in, it bends towards, it comes out, and it comes out. So it looks like this object, this mirror, is not as deep as it would be, or should say deeper than it would be. Swimming pools appear shallower. It really depends upon how they want to ask the question, I guess. Because this light would appear like, okay, let me explain it like this, because I don't think I explained it well. If this light was to keep going straight, and in fact, maybe I'll do a drawing. Maybe this will work out better with a drawing. So here's some water, and light comes into that water, okay? And it gets bent, and then it comes up, and then it gets bent out again. If I was to reconstruct these without going all the way down, right, they would intersect here. They would not intersect way down here. So my mind would reconstruct this and say, okay, this light is only that deep. That's what my mind perceives. But the light actually went all the way down here, came back up, and then got bent out. But my light doesn't know that bent, my mind doesn't know that bend happened. So my mind traces it back straight. So it looks shallow even though it's deep. There, I think that was better. So things always appear more shallow. Here you can see this, the virtual fish is not as deep as the actual fish. And so like if you ever spearfish, you always have to aim deeper and closer than you actually see the object, because that's where the object really is. Where you see it is not as deep, and so your brain says that it's like here, and in reality it's down lower. And sometimes your brain will, yeah, so you need to aim down below where the actual image is if you ever go spearfishing or something. And we call that apparent depth versus real depth. A mirage is sort of related to that. So a distorted image called a mirage is caused by refraction of light in the Earth's atmosphere. So let's say that we have this light and this tree is really way far away, and as the air bends the light, I see it. But my eye says that this object is right here, but in reality it's way over here. This is the same reason too. I don't know if I have an image of this. Yeah. Why it looks like the roads are wet. You're actually seeing the sky in the road. So you look towards the road, but because the light has been bent by the temperature changes, your eyes actually bend up and see reflections. And if you look at this image, you can see the reflection of the car there. And then where there's no vehicle, you're actually bending around and seeing all the way up to the sky. And that's why you get these mirages on hot roads. That hot air rising creates situations like this way back here where I have warm air, and as that warm air rises, it bends the light, it bends sound, it bends light, so that I see something up here. So that mirages are an example of refraction. And you also see atmospheric refraction. I've talked about how blue light is more dispersed, but actually as the sun is setting, you get this refraction of the light so that when the sun is setting, like when the sun looks like this, part of that sun is already below that mountain, but the light is being bent so that it looks like the sun is here, even though the sun is actually down here somewhere. That's because of refraction. And you'll notice how the sun does not look circular. It looks kind of flattened out. And that's also because of refraction. Okay, I think I'll keep going, but let's do this. If the speed of light were the same for different temperatures and densities of air, would there still be mirages? No, because if there wasn't a change in the medium, if there wasn't a medium shift, then there wouldn't be anything. Oh, and I just realized I left that up. So let me go back and show these images. So I was doing all this, didn't realize I was cutting off the images. Where's the image here? So warm air causes this bending. So if I have warm air coming off a hot road, just like sound gets bent up by air temperature differentials, if I go to this example here, you can see that this road creates a mirage where I'm seeing the sky that's actually being refracted off of this. So I don't know when I messed up and left my images visible there, but and then I know here you see how it's flattened, and the sun is actually down here somewhere, but it's being bent so that we see it. I mean, here's the center of the sun. I called it the moon, and here's probably where the moon really is, just down a little bit lower. So if the speed of light were the same for the various temperatures and densities of air, would there still be a mirage? No, because there wouldn't be any bending of the air. What causes the mirage? The bending of the light in the air. So that's diffraction and reflection. I'm going to stop, and then next video will be dispersion.